Yeah, okay.
Okay, so I think before you even pull anything out, let's do this the easy way.
Yeah.
Tell me about the relationship between robustness and explanation.
Okay. Robustness and explanation actually is really multiply connected. On the one hand, robustness is really connected, as Richard Feynman said, to fundamental aspects of physical nature. Feynman, in his book *The Character of Physical Law*, argued that the fundamental principles of nature are remarkable because they're derivable in multiple ways from using multiple different assumptions. So in some sense, they're almost unavoidable. They don't depend on any particular result. There are other things. It turns out that great conservation laws in physics have the same character. They are deeply anchored, therefore, in the explanatory frameworks we would use for even deciding what's a reasonable explanation and what isn't. But secondly, down at the sort of nitty-gritty of ordinary level explanation, I could be sitting here, well, I never stand behind a podium. I pace when I walk, but when I lecture. But if I'm standing behind a podium, I use this to illustrate the point. I smack it on the side and you hear it. I feel the sting in my hand. It's impenetrable. Visually, you can see that you can't see the lower part of my body if it's behind the podium, so I can detect the podium in multiple different ways. So robustness is fundamentally connected with the objects that we see in the world and need explanation. Furthermore, the objects that are detectable in that multiplicity of different ways also are things that are connected to other things. They have multiple properties, and being detectable in these multiplicity of ways are likely to be connected to more phenomena. So if you want to start out with sort of central things to move out from in organizing explanatory schemes, they're going to be important things to use. And that applies not only to objects on different scales, but to the levels of organization themselves. That is, if levels of organization are the, as it were, joints of nature, Plato suggested we should cut nature at its joints, that ought to be the aim of knowledge and of science. Well, then levels of organization are going to be composed of things which you get the largest order out of theorizing about. And what are those going to be? Well, those are going to be the things that are most richly connected to other things and which therefore have regularities about their behavior. In fact, here's another way of putting it. If levels of organization didn't exist as sort of foci of stability, because that's what they have to be. To be a level of organization, it has to be a perduring thing that can be modified in various ways, but still is, as it were, always there. If they didn't exist, our evolution could not have happened. That is, evolution requires that there be stabilities in nature which you can utilize in building species that can evolve. You need stable building blocks, as it were, and it applies all the way up. Stable systems made out of building blocks, stable super systems made out of subsystems, and so on. So there are, I think, multiple connections between robustness and not only what there is out there, but also what we ought to use in explanation.
Okay, that was great.
Okay.
See, that works, and you know, it's separate from the slides. It allows an introduction to the slides without, yeah. All right, let me think of one other one to ask you along the similar lines, because that was great.
Yeah, this works a lot better.
Yeah, by the way, you're shorter and more to the point when you don't have the slides there.
Yeah, I know. That's too bad. I realize. I mean, what happens is you build a slide set because you want pictures to illustrate the kid. Then you have to stick text in there.
Right.
And then you have to transition from one to the other, and it gets Yeah, you're right.
What would the relationship be between robustness and final cause?
Oh, boy. Um, Between robustness and, can I turn that into a question between robustness and function?
Yes.
Okay, that's good, because I can actually talk about entrenchment. Okay. Entrenchment, look, consider any adaptive system, or consider any machine whatsoever. The machine has differentiated parts, and its performance will depend in different ways on what those parts do. Which means, for most interesting machines, there are parts which, if they break, don't cause much damage, and you can pretty well use it without them. Maybe you can't do quite everything you could before. And other parts, which if they break, you're dead in the water. You just can't do anything. Okay. So some parts have a bigger effect in the downstream. They have more downstream consequences for the operation of that machine than anything else. Well, that turns out to be an extremely general principle of organization. It applies for artifacts, it applies for organisms, it even applies for ecosystems. So-called keystone species are those that, if you lose them, many other things collapse. In fact, I think it can arguably be said that it applies to any functionally organized system, any roughly adaptive system, any system that's a product of a selection process, that in order to accomplish any sorts of complicated functions, it will be differentiated, it'll have different kinds of parts, and those will have differential impact. Now, suppose you ask, are there any ways of getting away with making changes deep in the functional architecture? In fact, actually, that's just what happens in science. When you have a scientific revolution, what you do is you change the base principles. And that forces you to make changes all the way up, as it were. So, for example, the replacement or the relation of Newtonian mechanics to special relativity involved the Lorentz transformations. And all of those involve saying, you know what, classical kinetic energy isn't quite what we thought it was, and various other things change and so on. But you know what, classical kinetic energy, you get relativistic kinetic energy from classical kinetic energy this way. First of all, there's the rest mass, but you only release that as energy if you do mass-energy conversion. So that takes a very highly energetic reaction. And then there are these ascending terms in powers of the speed of the system divided by the speed of light. And if the speed of the system is small relative to the speed of light, those are all negligible. So you know what? If you're building bridges or locomotives or flying airplanes or so on, you just throw away that big term of the rest mass and you ignore the higher order term of that happen as you're moving close to the speed of light, and Newtonian kinetic energy works just fine. Now what I did is I sketched a really fundamental transformation at the bottommost level, but it works. Why? Because it preserves all of existing Newtonian theory, except for some around at the edges. And in that way, that's a result. Classical Newtonian mechanics is going to have to be preserved more or less in any future scientific revolutions, because it is itself robust, and it will have to be preserved to anything else. Well, let's look back now at function and ask, what role would those basic principles play? And the argument is that any transformation replacing those basic principles, whatever other things it may be able to do, had better be able to preserve those things. And that actually works for deep modifications in genetic programs too. You can get away with a deep modification in genetic program as long as you preserve the most important functions of what you're replacing. That's how the computer was able to replace the IBM Selectric. It couldn't do so with the Apple II. That was a 40-character line. And even though you could do spreadsheets with it, and that was, as it were, the killer app that made the personal computer, it didn't really become a replacement for office machines until you had the IBM PC with an 80-character line and a daisy wheel printer that could produce letters on stationery, and then it could penetrate much more deeply. So, and then, by the way, while you were at it, it also was open to doing other things. It could be expanded to give you email access and internet access. And all of a sudden, it could take on a whole bunch of other functions. And so the computer became ever so much more deeply entrenched in the same way, with lots of downstream consequences, than the typewriter, but was able to substitute for something that was absolutely central to the business community by meeting the sort of functional constraints that it required. Of course, that wasn't quite complete. We had a director of information technologies here that came in and when Apple was at a low point, wanted to do away with supporting Apple and switch everybody over to Windows machines. That was all well and good in the business schools and so on that were using them, but it turned out in both the social sciences division and the humanities division, there were a lot of secretaries that had learned on the much more user-friendly Macs. And they threatened to resign en masse if he stopped supporting the Mac. So the Mac became became sort of preserved in that case, even when its fortunes were very low, not because it had preserved all the basic functions of the typewriter that the Windows or MS-DOS as it was at that time preserved, but because it was so much easier to learn than MS-DOS, and the secretaries did not want to have to change to learn the new operating system. So that relates entrenchment and robustness, in this case of function, and what you can do to get away with making deeply entrenched changes, which is, of course, something we really need to know in complex systems. How do you get away with, and by the way, you can't always get away with making deep changes because there may not be an accessible alternative substitute. But if you're going to do it, that's how you have to do it. Is there something else you wanted to pursue in that direction?
No, that was good. I think, okay, here's one more, and I think we've got our great set of snippets.
Okay.
What's a good explanation? What's a bad explanation?
I would say a good explanation ought to be something that is not too sensitive to detail and is potentially generalizable. And I don't mean by that you can get a general law out of it, but that it can apply to at least some range of other situations sufficiently like it. Let me put it this way. If a phenomenon is so special that you only get it under exactly this set of very complicated situations, then it's probably not going to recur again. So it's not something we need to be interested in. And we aren't even going to detect things that are that sensitive. We can theoretically show that there are things that are that sensitive with nonlinear dynamics and chaotic systems and so on. But even for chaos, there are molar statistical regularities in the behavior of chaotic systems. And there are ways of controlling them in terms of modif feedbacks acting on their short-term behavior, which is more controllable. So, so I would say that's an important constraint. That is, it ought to be, it ought itself to have some limited generality, But on the other hand, I think there are regularities in nature that are what I call sloppy, gappy generalizations. That is, you never get the noise and the regularity down below a given level. And furthermore, there are holes through which, regions as it were, in sets of parameters for which the explanation at that level breaks down completely. And you have to go to a lower level or sometimes a higher level. For example, classical thermodynamics in ideal gases as fluids works very well. Except there's this phenomenon in which you can actually see it breaking down, called Brownian motion. And if you learn something about Brownian motion, you can learn some really quite fascinating things, both about our visual system. An insectivorous songbird will see a jaggier Brownian motion than we would, because it is seeing things at 70 frame flicker fusion of 70 frames a second rather than our 24. So Brownian motion is in a way scale dependent. Why? Because that bird is able to track shorter zigzags in the motion resulting from local imbalance of bacteria-sized particles with molecular collisions. So in fact, Brownian motion is fascinating because it's a kind of between levels phenomenon. But there are no other entities of its same size, because if you ask, well, what causes a zig or a zag in Brownian motion? It's a local statistical fluctuation in the number of molecules hitting it on one side or another that fail to average out. And it can do that because it's small enough that the large numbers effect don't damp out. And tells us, therefore, that there are molecules down there. And that for some purposes, we need to look at the lower level as well as the ideal gas law. Well, nature's full of those things. And in fact, as human beings who can interact with nature in multiplicity of ways, we tend to see more of them. And in fact, for evolved systems generally, given that selection works on an average statistical advantage, selection doesn't need absolute regularities. And so we should expect that evolved systems won't generally have them. Except, of course, for things that are deeply entrenched. And as it were, the more deeply entrenched something is, the more it becomes quasi-categorical and invariant. Why? Because smaller and smaller changes in it can make a significant difference as it gets more entrenched. So.
And then what's a bad explanation?
A bad explanation would be one that, well, look, there are a lot. Let me draw a parallel. There's only one way of having a linear function, but there are lots of ways of having nonlinear functions. Okay, so people don't try to classify nonlinear functions, at least in the same way, or they often start. Let's start by assuming a linear function. Okay. Well, if you ask me what's a bad explanation, there are all kinds of bad explanations. If you have to meet a number of constraints to meet a good explanation, I mean, I've ignored many dimensions of what counts as a good explanation. So, for example, if you insist on giving it an explanation in terms of, say, the second derivative of a function, and you're talking to a high school algebra class, that's a bad explanation for that context. It may be a good explanation to a calculus class, but it's the wrong explanation to the audience. So you have to recognize then that you have to give the audience the background knowledge, if necessary, to appreciate your explanation. And here's another problem. If they disagree with some of your background presumptions, you may not be able to get started to them. Now, that's then treating explanation in a different way than I was before. I was talking about what's a good explanation from a, let's say, I would call it a robust realist perspective. You would call it a robust pragmatist perspective. I think the two are probably pretty close, maybe identical. But in fact, what I was then doing is exploring the issue of what's explanatory to a given audience. What is likely to convince them? We're struck in looking at the sort of irrationalities in probability assessments that Tversky and Kahneman gave us by the importance of salience in an explanation. So people are far more worried about an airplane trip than they are about a car trip, even though the casualty rate in car mileage is more than 100 times as great as it is for air mileage. But on the other hand, car crashes happen every day, and you know people, in fact this ought to be an indicator, almost everybody knows someone who's been seriously injured in a car crash. I defy you to find someone who has been, no, you may know someone who has been killed in a plane crash or seriously injured. Now, if you formulate the problem that way, then you're led to describe it in a way that maybe gets you plugged into the frequency in the right way. But salience, how juicy a story it is remarkably effective. So.
Okay. Any words of wisdom for our conference audience?
Oh boy. Yeah. Recognize the importance of taking multiple perspectives on a problem, because we don't have any perspectives that cover all the waterfront. But the problem is not just taking multiple perspectives as, well, you could do this, you can do that, so therefore you can be a relativist. The problem is to realize that each perspective will contain its own, as it were, truths or revealing facts, if you want to describe it that way, and also its biases. So the problem is, how do you get all the perspectives together, as it were, to rub off the biases? That you can do if you have a number of people from a number of different perspectives and get them to sit down together and work on a problem. That doesn't always work, though. If they're too different in perspective, they may say, I'm not going to sit down with them, I don't accept it. This is often a problem in communication between people in the humanities and people in the sciences. That too many aspects of their worldview are too different. It shouldn't be. And that actually is one of the great benefits that we used to have in a liberal education. Of course, now we've watered down science for the humanists, and sometimes, unfortunately, in the aims of pre-professional education, watered down the humanities for the scientists and the professionals. One of the ways in which Europeans have admired American post-secondary education is our the greater breadth of our educations. But if we give it away, we don't have it anymore. And from what I understand, businesses are more interested in hiring people who have the capability to acquire professional training, but the judgment that comes from broader exposure in literature and humanities. Of course, if you put off acquiring any professional competence or any math or science until college, it's already too late. You don't have you're not dead in the water, but you have a very hard row to hoe, because you have to learn how to see things through that lens.
Good.
Okay.
Yeah. I think that works.
Okay, good.
See, that was simple.
Yeah, okay.
No.
All right. This time, hang on. We're not
And-
gonna,
and-
we're,
oh,
not,
now look.
we're not leaving until I make sure I pack the things that I'm supposed to pack.
Now, there is one important thing, and that is, if you're going to want to edit my slides, which I think you are going to want to.
I'm still sending them to you first.
What?
I'm still going to send it to you
No,
first.
what I was going to say is, what you're going to need to do to edit it is modify it in Keynote on a Mac, or tell me which slides you want to cut out, and I can do that. send it
Yeah,
back.
well, or, I mean, I actually have, believe it or not, I have a PDF to PowerPoint converter that's going to take your PDF and is going to make it a PowerPoint.
Oh, okay. Really? Okay. Yeah. Oh, that doesn't surprise me actually. By the way, I'm very. I didn't mention actually one of the best examples. Platform independence. So the desire for platform independence is exactly allowing change or allowing generalization over something that used to be deeply entrenched. You and I can remember what it was like to be wedded to a particular operating system and the software for that and sort of extreme limitations. But the search for platform independence.
It doesn't have an on-off switch.
What?
It didn't have an on-off switch.
Is it on? Was it on?
It was on. I was trying to figure out how to shut it off.
Hey.
And the answer is you have to turn the batteries upside down.
What?
It's on when the batteries are in the right way. It's off when the batteries are not in the right way.
Wow.
So they don't have an on-off switch. There's a stop switch, but the stop switch did not turn it off.
That's amazing. How much did this cost?
$89. The last one cost $89. It's not like I've lost something huge. I
Yeah.
mean, you know, I lost an hour and a half of our time, but I didn't lose
Yeah.
something that was particularly expensive.
Did you lose Tim Allen's thing too?
No, Tim. See, Tim and I were rehearsing because Tim is coming. So Tim and I, it was just trying to get Tim down to.
Oh.
Tim's issue is a simple one.
Yeah.
Tim has a real hard time with the idea that he's only allowed 40 minutes.
Oh. I remember now. I got him down here to talk.
All right, so that was Tim's issue.
Yeah.
Was I can't do it in 40 minutes unless we rehearse. Tell me what to cut out.
Yeah. Right.
Because he started off with 3 hours.
Ay, ay, ay.
And I was like, no, that won't work. So let's see. I think I just-
Well, I